Alrighty, that screens are working. Beautiful. Technology is actually working. Okay, so for the last, I guess, 30 minutes of this class, so I'll get your quizzes graded and back to you by Wednesday, so that you have that to study for the exam. Hopefully you, as you're talking to other people, lots of people got the same number, which is a good sign, because that's the same number that I got. But that's good, because it wasn't like, it was a weird geometry and a little bit different of a problem to think through. So hopefully you feel good about some of that. Like I said, I'll get it back to you so that you can see if you did get it right or if you got it wrong, kind of where you went wrong. I'll get that back Wednesday. What we're going to be covering the rest of today and on Wednesday is going to be things that are new and important, but not on the exam. Right, so the exam is on Friday. If between now and Friday something comes up where you have to take it virtually, reach out to me and we'll kind of go through, we'll come up with an option that works for that. But other than that, if you don't reach out to me, I'm planning on you being here Friday and taking the exam, and that will be Friday. So today, what we're going to try to do is we're going to take a problem that was simple and that you could all do in about 15 minutes, and we're going to make it uglier and more complicated, just like we love doing. Right? This is what we do. But we're going to do that because we're going to make it from, like, right, we're going to take something that's simple and that you can kind of do by just rationalizing it in your head and thinking through it. We're going to take it and say, like, what did we actually do? And let's put it in the language of math, and specifically in the language of calculus. So we'll hopefully try to figure out, like, how did we actually do this problem in the language of calculus, so that then we could do any problem. Right? What did we actually do? Well, we used conservation of mass to be able to look at how much mass is coming in, how much mass is going out. We know conservation of mass means that mass is not created or destroyed, so that meant what comes in must go out, right? So this is kind of how we rationalized through that. And we found how much mass is coming in. We found by velocity times area, that gave us a volume, times density. That gave us a, like, how many kilograms per second comes in. The problem comes when we actually try to, like, take that and generalize it to any system or any arbitrary system. So that's what we're going to work on today, is trying to take this and write it in weird, goofy looking notation. And then we'll try to, like, back up again on Wednesday and say, what is it? How do we actually take this weird, goofy notation and actually solve problems with it? So we're going to take a simple problem, make it a little bit more complicated, but hopefully in the end, that gives us more flexibility with what we can solve. We can solve things that we can't just, like, think through and rationalize our way through. We'll be able to solve more complicated things, more interesting things. Okay. So this is moving from, so statics, it was chapter 3. We're going to be moving from chapter 3 now to chapter 4. And our discussion is going to be, we'll call it Reynolds transport theorem. Okay, so that's what we're going to be talking about in chapter 4, this thing called Reynolds transport theorem. And we won't define it today, but we'll at least kind of get started on our way to what that even is. It's a way to be able to use, like, physical laws like you would in physics on fluids. So, okay, what do we typically do? We typically apply physical laws to a mass. To a mass, right? If we wanted to say, okay, conservation of energy, we would look at a specific amount of mass and we'd say, you know, we'd look at that. If we wanted to do conservation of momentum, we'd look at like a specific mass and we'd say conservation of momentum on that mass, and there's like a force acting and a force, you know, we're going to do F equals ma. We would look at a specific mass and we say, what are the forces? What's the net force on this specific object? And kind of go from there. So we typically, this is how we, in physics class and other engineering classes, typically we're saying, we're looking at this object and we're looking at forces on it, we're looking at energy in it, like something, but we're looking at a well-defined object. So this would be what we call the system approach. Or the control mass approach. So this is like normally how we apply the laws of physics. Right, if we were to do something like this in fluids, what we would do is we would track a particle of fluid, or particle or a group of fluid. So we would, for example, we would look at, draw it a little bit better. We would look at this chunk of fluid and we would say, okay, it's right there at time 0 and something's going to happen to it. Forces are applied, like different, and it's going to move somewhere else. So we would look at this, right, moving from there to say there. Basically, we're trying to watch where it's moving, this single group of fluid, or this single like group of fluid particles. And if, for example, with conservation of mass, we would say the mass of that object, the mass of that chunk of fluid doesn't change. If we were looking at F equals ma, which we will later, we would say, okay, the forces on that object, that's going to be related to the acceleration of it as it moves. Okay, so we would have something of defined mass and we'd watch it move through a fluid, something like that. What we did when we solved the previous problem is we did not actually track. So when we solved this, we could have tracked the fluid coming in and watched where it went, and it's going to have to, like, that particle is going to come in and it's going to have to come out somewhere, and we could track, you know, where it comes in and where it goes out. That would be one way to look at this, but it's in fluids, a lot of times it's easier, not all the time, we'll actually use both systems, but a lot of times it's easier to, rather than like watch an individual particle come in, say like come in this side and end up going out that way. We're not going to track an individual little particle, you know, as it moves along its merry way. We're going to instead do what you guys did, which was say, we're going to look at this volume, and we're going to say what's coming into that volume, right? This volume here, what's coming into that volume and what's leaving that volume. So a lot of times in fluids, we're going to watch a specific region of space and say what comes into that region of space and what goes out of that region of space. We're going to do it with mass like you did here, but we're also eventually going to do it with things like F equals ma, with momentum, and with energy. Right? We can use the first law. You could do it with other physical laws too, to be able to get an understanding of how fluids move and flow and how forces work and all of that type of stuff. So that's kind of what we're building to. So the system approach, that's how we normally think of physical laws. A lot of times, a more useful approach for fluids is a control volume approach. Okay, so right, in a control volume approach, we are going to watch a specific region of space. Okay, and that's how we're going to be looking at the problem. So all of our physical laws change a little bit. Because if you think of control, conservation of mass, that's the easiest one. Conservation of mass, that means if you have a particle of a certain mass, the mass doesn't go up or down, it's conserved. If you have conservation of mass on a specific region of space, now you have to say, okay, what's coming in and what's going out, and is there any accumulation inside of our region of space? You have to account for more things. So that's what we're trying to do, is say, like, take something, how does that work? How does conservation of mass work for an individual particle? Mass is conserved. And then how do we expand that to, like, watching some arbitrary region of space? So this would be, just to draw kind of a simple picture, we would have some region of space where this is our CV. It doesn't have to be a box. And we would have flow kind of going through that box. And we would be watching the box, not really watching the flow. So the first one, we're watching this particle. So this is our control mass particle. We're watching that particle move through space. The second one, we're watching a region of space and watching things move through that region of space. There's kind of a subtle difference, but it will become important in how we think about it and how we use that. We'll end up using both of these approaches, but we'll start with the control volume approach. And that's what we're going to work on in this for the next while. Okay. So if we wanted to write an equation for this, in words at least, we could write that. So we could look at the CV picture. So we're going to say that this is a region fixed in space. So it's stationary, just like a set region of space. And I'll write, for now, eventually we can actually take that region of space and we can move it. Sometimes that will make our lives easier. For example, if you want to figure out, like, thrust from a rocket engine as your rocket is taking off, your rocket's moving. So if you just are, like, looking at the launch pad, a couple seconds later, your rocket's not anywhere near the launch pad, and you go, well, that's dumb. Like, you should follow the rocket. So eventually we'll get to, like, we'll actually move along in space. But for now, it's a fixed region. Okay, so it's, we're going to look at a mass moving in or out of our control volume, moving in or out, like crossing the boundaries of our control volume. And if things are moving, they're moving with a velocity. So we're going to have velocity measured relative to CV surface, what we'll call the control surface. Okay. So I'll draw a kind of an arbitrary picture that hopefully will help us think through this a little bit. So this is a, let me draw that better. I want to draw a shape that I can draw that looks like a lima bean because I can draw that twice. So this is initially at time t0, the initial time. Okay, so this is our that's our control surface, the black line, the surface of our thing, of our shape. The shape itself is the CV. We, in general, have like fluid is moving in and out of that, so we can draw, just for the sake of drawing it, we can draw some flow kind of superimposed on top of that. Right, those would maybe be the streamlines. Okay, so initially we're going to say, okay, this is what our control volume looks like. It's in a flow. It's this funny lima bean looking shape. Let's take a snapshot there, and then we'll take a snapshot a little bit later and see what happened. So a little later, at t equals t naught plus a little bit, plus d time. Okay, so if we try to take the same shape, and I'll do my best. That's not very good. Try again. Maybe okay. You can tell it's at least supposed to be the same shape. Okay, so what happened a little bit later? Well, our fluid moved. How did it move? It moved, well, here's our velocity still. Say that didn't change. Okay, so the fluid is moving that way, kind of along with those velocity vector lines. So then again, I'm just going to kind of eyeball this, but I think you'll get the idea. This would be something like that. So our initial fluid is the dotted line. Our CV is still the black line. So we would have here and here. This would be, put in blue, this is we have kind of new fluid that's entered into our control volume. Okay, and then here, we had fluid that left our control volume, or fluid that went out of our control volume. What we want to do is write this in calculus. Okay, calculus and vector notation. So we're going to have I guess two things. We're going to have to be able to look at what's inside of our control volume. That's what we care about, really. We're going to have to be able to look at how does that change if it does, because in general we could have more mass building up inside of our control volume, or like mass changing with time inside. Conservation of mass tells us we can't have that, but that's okay. Like we can have more mass flow into our tank, for example. If our control volume is a tank, we could have more mass flow into our tank. So we have to consider that. We have to consider how much is coming in to our control volume, and how much is leaving our control volume. We can do that, the flow rate in, flow rate out, we can do with, just like you did on the in-class thing, it was density times velocity times area. We just have to make it more general because we may have any different shape and any kind of velocity. So that's kind of what we're trying to build for. So let's write this in calculus. So let's write the general conservation of mass equation for a CV. So we have to start with what is just the physical law for conservation of mass. So how does mass change with time for a system, for like an individual particle or an individual mass? How does mass change with time? It doesn't, because it's conserved. So this is equal to 0. So this is like the physical law. Right? And again, as we start to expand this to other physical laws, right? Not everything is a conservation law, but we're going to have to look at, okay, what is the actual, like the fundamental physical law that we're looking at? In this case, mass is conserved. So that would be here, a 0. This is the telling us that for a system, mass is conserved. So in the universe, mass is conserved. Okay, that equals, well, there's going to be potentially accumulation. So how would we track accumulation? Again, in kind of our general generic shape, we'd have to look at the mass of the stuff inside of this shape. So how do we do that? Well, we would take the density of the stuff and add it up over the whole volume. But potentially that could be different at time 0 versus, time a little bit later versus time a little bit later. So that could be changing with time. So what we're going to do is look at the, not d, dt, the time derivative of, okay, we're adding up density over the volume, so that's an integral, over our control volume, over the whole shape, density d volume. Okay, I told you that we were going to get to kind of like weird notation to make a simple thing hard. Eventually we'll make hard things simple, but first we have to make simple things hard. Okay, so that's, what is that? That's the rate mass That's the rate mass accumulates inside of our control volume. Then the second part, we're going to be watching what? We're going to be watching mass come in and mass go out. Okay, so we're going to say mass could come in, mass could go out. That's going to be related to, just like in the example that you guys did, that was density times velocity times area. Okay, that was the mass flow rate in or the mass flow rate out. We're going to be doing, okay, so we're going to be doing velocity times area times density over the whole like outer surface, because we're trying to look at what's crossing that outside surface. So that's going to be another integral, this time over what we call the control surface of density, velocity, dot, dA. So that term, this is the net mass flow out of RCV. Okay, so across that boundary, across that surface, which we call CS. So for example, like the fluid that moved from right here to right there didn't leave. So we don't count. We're only counting the stuff that I shaded in this example, the stuff that actually came in or the stuff that actually left. So I told you it would take a simple thing and make it ugly and hard. So I wasn't lying. This equation, this is the continuity equation. So it's really like conservation of mass. We often in fluids will call conservation of mass, instead of that, we'll call it continuity equation or continuity, meaning like the stuff can move, but you can't like magic stuff out of thin air or have that stuff disappear. So you have to be able to track it, and it has to be able to obey conservation of mass. Right, all it's saying is that, right, 0 equals mass accumulated plus mass out minus mass in. That's all that, right? It's this kind of goofy looking notation, but that's really what it's saying. If you look at it, at least in words, that hopefully jives with what you were trying to do in this in-class assignment. Yeah, Brennan? So if you were imagining like filling up a tank with water, if your control volume is your tank and you have like, one hose coming in and a leak at the bottom, you could be filling it up. How much is coming in? How much is actually filling up inside of your tank? How much is leaving out the leak at the bottom? So you're going to be having potentially all of those terms. In the system that we solved, there wasn't an accumulation term. It was just what comes in must go out. So often we'll come with into that special case. So all right, we'll just finish this. A special case of this, and we're not going to get to an example today, but a special case is if we have steady state flow. And density is constant. So if these two things are true, if it's steady, if the flow is not changing with time and density is not changing with time, then we get, right, 0 equals d dt rho dv. Things would not be changing with time, so this whole term would be equal to 0. Rho v dot dA. So for this special case, we would get 0 equals integral for a control surface of rho v dot dA. So this is what you guys all solved. You just did it without kind of starting from the strict math notation. You just did it because you could figure it out in your head. So the challenge is, we have kind of two challenges. One is to kind of be able to get from this weird math notation to the actually figure out how to apply it to a system that you could already solve in your head. So why do we make it more complicated? But we did that because we're going to say, okay, now this framework can be now applied to anything, things that we couldn't just think through and get to the right answer in our heads. So that's going to be our challenge for the next couple times, is how do we take this, apply it to other physical laws, apply it to weird kind of processes, figure out how to use some of this weird notation. So we'll continue with that on Wednesday. Again, not on the exam, but see you back. Hope you have a good Monday, and see you back on Wednesday.
I'm going to go run and get that quiz copy real quick.
Thank you. Thank you, sir.